let's get started. So at this point, we've finished the first part of the course, which also means that there's a quiz coming up next week, which hopefully all of you are aware of. So I put the details here of where and when the quiz is. It's going to cover everything up to lecture 8, so not today's lecture. And if anybody has conflicts, you can either post to us on Piazza or just send an email to the staff list. Okay? Any questions about logistics before we get started? Great. All right, so today we're going to move on to talk about programmable machines. So what have we done so far in 6004? So far we've learned how to build combinational circuits, how to build sequential circuits, and together we're able to put them together and make some kind of special purpose hardware which solves problems like modulo 4 or GCD, and we've seen how to do that. And the general picture that we've seen of how to do that is that essentially we use some registers shown here in order to hold the state, and then we have some combinational logic which takes as input the current state as well as any inputs, and it produces the next state and any outputs for your circuit. So what we're going to move on to in the second part of the course is we no longer want to be focused just on a specific special purpose hardware, but rather we want to move on to building a general purpose computer that could solve any computable problem as long as it has enough memory and enough time. All right? So that's our goal for this next section of the course. All right, so there are many ways to build a computer, but if you look at modern processors, almost all of them use the von Neumann model, which was presented by John von Neumann in 1945. And what this model looks like is the following. It's got 3 components. The first is main memory. Okay, so main memory is used in order to hold your programs as well as any data. And the main memory, it communicates with our central processing unit, which is basically the smarts of your computer, which is able to access and process these memory locations and do the appropriate things with them. And then the third component is an input and output component, which allows you to interact with the outside world. We're not going to focus on this part until much later in the course. So for now, we're going to be focusing on how does a central processing unit work together with main memory. All right, so we've talked about storage already, and we learned that we can use registers in order to store information. So we've seen individual registers, as well as we've mentioned a register file, which is a combination of registers that are controlled by the same enable. And the problem with just using registers, however, is that it quickly becomes very costly to have more and more registers. So we're only able to hold a small number of registers in our CPU, and that's not going to satisfy all of our storage needs. So here comes, main memory to the rescue. So main memory, when we talk about it, we refer to random access memory, and it looks something like this. It's basically an array of bits, which is organized as W words. Generally, W is a power of 2, and each of those words is n bits wide. Okay, so in this example, we've got 8 words, each of which is 32 bits wide. And so in order to access the particular location in memory that I want to access, we need what's called address bits, something to specify which of those 8 words am I trying to access. So if I have 8 words, or 2 cubed, that means that I need 3 bits of address to specify which of those locations I want to access. So using those address bits, I can say, okay, if I'm trying to access location 001, I now have the ability to both read and write the entire word that's located at address 001. Okay? Now, as far as implementation of memories, we're going to get into that in a later lecture. Today we're focusing on what the processor looks like and how it goes about interacting with this memory. Okay, so far we said, until now we've been using registers for any storage. So now we kind of want to change our conventions a little bit because we only have a limited number of registers. So essentially, if you have a program, you can kind of think of your variables will live in your main memory, and then your registers are going to be used to store temporary values, or they're going to be used to store, some values that you want to access repeatedly. So the ALU operations, however, in the ALU that we've built, are going to work only on the registers. They can't work on pieces of data that come directly from the memory. So in order to operate on things that come from memory, what we need to do is we need to first load the value from memory into a register. Then we operate on it using our ALU, which can get information from the registers. And then we need to take our result and store it back into memory. So what does that look like? Suppose that I want to do, this simple expression here, which says y is equal to x minus 37, okay? If, as I mentioned, I have my x and y variables living in my memory, and in this particular example, x lives at address 0x1008, and y lives at 0x100c. And so what I need to do in order to perform this operation is I first have to load the contents of memory location 1008 into some register, let's say register 1. I then subtract 37 from that register 1, and I can store it again, the result, back into register 1 or another register if I wanted to. And then I take that final result and I now have to store it back into memory, and in this case I want to store it into location 100c because I want to store it into variable y rather than x. Okay? So that's basically how we're going to be interacting with the memories, and it's very important for you guys to keep in mind always the difference between when you're doing things with registers and when you're doing things with memory. So whenever you're getting something from memory, you have to always access it through loads and stores. Okay? Any questions about that? Great. All right, so another way of thinking about our von Neumann computer is a stored program computer. So what do we mean by that? What we mean is that we have our instructions and they get encoded into our memory. And our memory is going to hold both instructions and data. And then our CPU is going to be responsible for fetching these instructions, figuring out what it is that the instruction is supposed to do, executing that, and then storing any results back to memory. So in main memory, we have both instructions and we have data. So what does an instruction need to contain? Well, an instruction needs to give me enough information so that I know what it's asking me to do, right? So here's an example of a word in memory, which is going to have some encoding of an operation I want to perform, a destination register, and 2 source registers. And so what this instruction is telling me to do is essentially perform the operation on your 2 source registers and store the result into your destination register. Okay? Pretty simple so far. Well, what about our data? Okay? Our data is just a bunch of binary. But if we look at the instructions, once we've encoded them, in order to specify all the registers and what, operation we want to do, it's also just a bunch of binary bits. So how do we differentiate between instructions and data? Yeah?
Do we have a bit that we know is the separation between where we have instruction and where we have data?
No, in fact, they can actually be interleaved. So this picture is not completely accurate in that data can live between your instructions as well, and depending on the situation. Any other ideas? Well, basically, the way it works is as follows. Our CPU, or central processing unit, actually consists of 2 separate parts. It's got a data path and it's got a control unit. So the control unit is the part that's going to fetch our instructions, interpret them, and then tell the data path how to execute those instructions. So anytime an address is sent to main memory from the control unit, that means that it's fetching an instruction. Okay? So what comes back from main memory is interpreted as an instruction. On the other hand, if we're executing something in our data path and we need to access some piece of data, then that address is going to come from our data path. And so anytime the address comes from the data path, we interpret that as data. Okay? All right, so let's take a little bit of a closer look at these two different pieces of our CPU. So first of all, we can kind of think of the data path as being your muscle or doing all the heavy lifting. And the control unit is your brains. It's basically telling the data path what it is that it needs to do for every single instruction. So the data path looks something like this, which we've seen, before. So basically, what do we have here? We've got a bunch of registers that we use in order to store some temporary data. We've got an arithmetic logic unit, or ALU, which is able to perform some variety of different functions, and the one that it performs is specified by this FN control signal. And then here we have two muxes, which are controlled by A cell and B cell, which basically specify which of the registers I want as my two source operands. And then dest is going to specify which of the registers I want to write to. Okay? Any questions about that? Good. So what about the control unit? The control unit, as we said, is responsible for figuring out what instruction I want to execute and interpreting, these bits that are coming from memory into, work that the data path has to do. So the way this works is as follows. We have a special purpose register called the PC, or program counter, which stores the address of the next instruction that you're about to execute. So the first thing that the control unit does is it sends a request to memory to load whatever is pointed to by this PC register. Okay? And so the instruction comes back to this control unit, and now it's the responsibility of the control unit to decode this instruction and generate the appropriate control signals for the data path. So for example, suppose this was our instruction where what we're trying to do is add R2 plus R3 and store it into R1, then the control unit would set A select to be R2, B select to be R3, and destination to be R1, and it would set function to be add, and in that way the data path would do the correct thing in order to execute this instruction. All right, so what's an instruction, and what kind of instructions do we want to support? So an instruction is basically a fundamental, it's a basic unit of work, okay? So in order to specify an instruction, we need to specify what's the operation that we want this instruction to execute, and we need to specify both source and destination operands for this instruction. So the way that a von Neumann machine executes an instruction is it repeatedly follows this the sequence of steps shown here. Okay, so this is what your CPU is going to do for every single one of your instructions. So the first thing it's going to do is it's going to fetch the instruction based on the address that's stored in your program counter. Once it gets the result back from memory, it's going to decode it in order to figure out which source and destination operands you're supposed to use, as well as what operation it's supposed to perform. Next, it's going to read the source operands. It's then going to execute the instruction. It's going to write to the destination operand. And finally, it's going to compute the next PC. So how do we compute the next PC? Typically, our programs are just stored in memory sequentially, okay? So computing the next PC essentially amounts to adding the size of an instruction to the program counter so that it now points to the next instruction in the general case. And we'll get to other examples in a minute. Okay, so what we're going to introduce today is what we call an instruction set architecture, which is a precise definition of what exactly is the interface between our software and our hardware, okay? And so what this is going to do is it's going to tell us, what operations does our processor support and what storage elements are available to us. So this concept of an instruction set architecture is a new layer of abstraction. And the reason that we introduce it, or that it's good, is because it allows you to really separate the development of software from hardware. So if we look at what an instruction set architecture does for you, it's specifying precisely what it is that the hardware provides, but it's not getting into the details of how it does it, right? So my instruction set architecture will tell me I have an add instruction supported by this processor, but it's not going to tell me how that add is implemented, whether it's a ripple carry adder or some other kind of faster adder. So, well, what's good about this? If we take a look here at these various processors from, 1970s to modern day, all of these implement the same instruction set architecture, which is the x86 instruction set architecture. So what does that mean? That means that a program that was written for this 8086 computer can run on one of our modern day processors, as long as it's also an x86. Okay, and so the advantage is it really allows us to separate the hardware from the software, and so you see here that throughout these years we've made tremendous gains in how fast our processors are, in the number of transistors that they have, etc. And so, but my add operation is still an add operation. It might work much faster on my newer processor, but it'll work, any program that worked before will continue to work today. So what's the downside of this? The downside of this is that instruction set architectures live for a really long time. And so sometimes when we make dumb decisions in our instruction set architecture, we also have to live with those for a long time. And so in fact, with the x86, there's a number of decisions that were made that today are still held as baggage because of the fact that the instruction set architecture lives for so long. Okay, so in this class, we're going to work with the RISC-V instruction set architecture. And for the rest of today's lecture, we're going to go through understanding what exactly it is that this instruction set architecture provides. And so this ISA comes from Berkeley, and it's got a bunch of different variants. We're going to work with the most simple of them. But so the RISC-V itself as a whole supports different data width. So for example, it can support 32 bits, 64 bits, or 128-bit wide values in the processor. It's got your basic integer operations, and then it's got some extensions, which are things like additional support for multiply or divide operations, or additional support for floating point operations, and so on. But for this course, we're going to focus on the simple RV32I, which is the 32-bit integer-based RISC-V processor. All right, so we said that our instruction set architecture tells us two things. The first is it's going to specify exactly what storage elements we have available to us. And the second is it's going to specify what instructions are available to us so that the software knows exactly how to interact with the hardware. So let's start with our storage. So the storage of the RISC-V is, we have a bunch of general purpose registers, and as we mentioned, it's costly to have very many of those. So we only have 32 of these general purpose registers, okay? In addition to those, we have the special register, which is the program counter, and everything else is going to live in main memory, okay? Now, it turns out that the constant 0 is used frequently enough in our programs that it's worth hardwiring one of our registers to give us always the constant 0. And so out of these 32 registers, x0 is hardwired to 0. So what does that mean? It means anytime I read x0, I'm always going to get a 0 back. If I try to write to x0, it essentially is like a no-op. It's not going to do anything because the x0 will continue to have a 0 in it, okay? All right, so, and how much memory do I have here? Where, again, our addresses are also going to be 32 bits wide. So if I have 32 bits of address, that means that I can access 2 to the 32 locations. Now our addresses, for historical reasons, are they're byte addresses, okay? So byte refers to 8 bits, and so for any address is always going to point to a chunk of 8 bits at a time. But our instructions and our data and everything is going to be 32 bits, right? And so at any point in time, if you think about the number of 32-bit units that we have, we actually have 2 to the 30 4-byte words supported by this 32-bit architecture. And so if you think also about the address of consecutive words in memory, they're going to differ by 4, okay? So we said that when we want to change the program counter to point to the next instruction, we would add to it the size of the instruction. And so what would that be in this example, in this particular processor? So if I want to go to the next instruction, how much do I need to add to my program counter? 4. Okay, so I need to, if I was at instruction 0, the next instruction is going to be located at address 4. Okay, and ignore the fact that here I've just shown 8 bits of address. You can assume that these are all 0 extended to 32 bits because our addresses are actually 32 bits as well, and each piece of data is 32 bits wide, and so is the data that's stored in each of our registers. Okay, so that defines the storage capabilities of our RISC-V processor. Now let's start looking into the instructions. So we're going to need 3 different types of instructions. The first are computational instructions. So those are things like add, subtract, things that our ALU is able to do. The second is because we have things living in main memory, we need to have what we call loads and stores. So some way of bringing data from main memory into our registers and back the other way. And finally, we're going to have control operations, which are going to enable us to change the PC so that it's not just always pointing to the next instruction, but sometimes we might want to jump around in our program. So why might I want to jump around in my program? If I have a loop, that's a perfect example, okay? So there are lots of different cases where we don't necessarily want to execute each instruction sequentially. All right, so our instructions, as we said, they're all 32 bits wide, and they look like this. We basically have a 7-bit opcode and a bunch of other bits, which we won't get into just now the details. But this 7-bit opcode is essentially defining a class of instructions. And so it's going to tell us how do I decode the other 25 bits in my instruction. So who can tell me why I might want to consider having a variable length instructions, meaning that they're not always 32 bits rather than having this fixed 32-bit? Any ideas? Yes?
I wouldn't know where your operation ends when you decode it with variable length.
Well, that's a reason why I wouldn't, but what's an advantage actually of having a variable length? Say that again?
Memory efficiency.
Exactly, okay? So it's possible that if I was to use a variable length instructions, that my programs would be smaller, okay? Because I don't always need all 32 bits of my instruction. But in order to make the decoding process simpler, we actually have all the instructions be of fixed width, and that width is 32 bits. All right, so we're going to now start to look at our computational instructions. So the first type of computational instructions are what we call the R type. So this refers to instructions that operate on 2 registers. All right, so this is the detailed encoding of what these register-to-register instructions are going to look like in memory. And so specifically, like all other instructions, they're going to have this 7-bit opcode, which is going to tell us these types of instruction. The encoding there is going to say this is a register-to-register instruction. And then we're going to have an encoding of our source operand 1, source operand 2, and our destination operand. And then we have some additional bits, which are labeled here function 3 and function 7, just due to the size of the number of bits in each of them. And those are going to be used to specify the precise operation that we want to actually perform. So is it an add, is it a subtract, and so on. So let's take a look at an example, and let's say we want to do an add instruction, okay? And so this is the encoding of an add instruction. We want to understand what exactly this encoding is telling our processor to do. So first of all, we've got these first 7 bits, which tell us, okay, this is a register to register instruction. And so that tells the control unit how it should parse the remaining bits in this instruction so that it knows exactly what corresponds to what. Okay? So the control unit knows that the next 5 bits are going to be your destination register and, and so on. And so if we actually take a look at what each bit corresponds to, we've got these 8 bits, which are going to give the operation that the instruction or the ALU is supposed to perform. In this case, it's an add. We have our destination register, which is encoding a 1 here. So this is telling us that our destination register is register 1. Our RS1 is set to 3, so that means that the first source is register 3, and the second source is register 4. Now, who can tell me why I have 5 bits for each of these register encodings? Yep.
Because you're mapping it to like one of the 32 bits of the you have 32 registers and you can map each of them.
Exactly. So I need 5 bits in order to identify which of the 32 registers I'm referring to. And this also alludes into another reason why we can't necessarily have many more registers, because imagine if you had to have 6 bits for each of those, then you very quickly start to use up all of your available bits of your instruction. Yes?
So you mentioned that opcode will instruct how to choose the things that we have to do.
Yes.
It's not totally clear to me how it's doing that here.
So this isn't showing you how it's doing it, but this specific encoding, 0110011, is going to tell the control unit the type of instruction that this is a register to register instruction. So based on that, it knows that the next 5 bits are going to be the encoding of my destination register. The next 3 bits after that are these function 3 bits. Then come my RS1, RS2, and function 7. Whereas if this opcode was something else, then the rest of these bits could be used in a different way. And so the control unit knows exactly how those bits are encoded for every different type of instruction.
And what about their lengths? Why does func 3 have 3 bits? Is like 3 bits wide, and why is like func 7 bits wide? Can it be different? Can they be placed in different areas?
Depending on the type of instruction that it is, yes. The one thing that is basically done in order to simplify the hardware is that wherever it's possible, the designers of the RISC-V instruction set architecture wanted to make the same type of bits map to the same location. Okay, so you're going to find that regardless of what type of instruction it is, your RD is always going to be in these 5 bits. Your RS1 is always going to be in those 5 bits, and so on. And so that leads to some of this fragmentation of why our operation is actually split up into 2 different fields. But the details of that aren't really what's important. What's important is you have this many bits, to specify what your operation is. You're going to be able to figure out what your, source and destination operands are, and based on this initial opcode, the control unit is going to know exactly how to interpret those bits. Okay? Any other questions? Yes?
Wait, why separate func 7 and func 3 instead of putting them together?
So it just has to do with all of the types of instructions that are supported by the RISC-V, and so it just makes sense because of the other things that are supported, that this is how they divided it up. You don't have to really worry about why, other than just to know that the reason that some of these encodings look funny is because they're trying to maximize this case where the same fields map to the same bits in your instruction. Okay? All right. So, as we said, what this instruction is telling us to do is to add the contents of register R3 to R4 and store that into register R1. Okay? Now, instead of, expressing this symbolically, it's generally easier for us to use a symbolic, instead of expressing it using, this arrow notation here, it's easier for us to use a symbolic representation. And so we're going to be using something always that looks like this to represent an instruction, which means add the contents of registers X3 to X4 and store that into X1. Okay? Now here are the rest of the two register type of operations that the RISC-V supports, and they're basically what you expect. They're they're the operations that we built into our ALU. And so we've got some arithmetic instructions, which are add and subtract. We have comparison instructions. This SLT stands for set less than. So basically what that means is it's going to compare your source operand 1, and if it's less than source operand 2, it's going to set the destination to 1. If it's not, it'll set it to 0. And this U ending means unsigned. So this is a set less than comparison. This is a set less than unsigned comparison. Then we have our logical operators, which are and, or, and exclusive or. And we have our shifts, which are shift left logical, shift right logical, and shift right arithmetic. Okay? All right. So, in addition to having instructions that use two registers, it's generally, it's very common to find constants in your programs, okay? And so it turns out that it's useful to also have a register immediate type of operation. And so instead of having, to put all of these constants always into a register before you can access them, there's another type of format which we call the register immediate, or the I type. And the way that this works is it's going to perform the operation on the contents of RS1 with this immediate constant and store the result into register RD. So what does that mean? It means that we have to somehow encode this immediate constant into our instruction. So we're not going to look at the exact encodings, but what I want to highlight is that based on, once we've used up the bits for our opcode and for our operation and for our destination register and for our source register, we have 12 bits left, okay? And so we have 12 bits to represent this immediate constant, all right? So that's going to limit the size of constants that we can use in our programs. And so finally, here's an example. This is going to take x2, subtract 3 from it, and store it into x5. And just like in the register-to-register case, we have a whole bunch of different types of immediate instructions. So you notice that they now have the letter I to indicate immediate. So this is add immediate, set less than immediate, and so on. And does anybody notice that there's an instruction missing here from the two-register case? Subtract. Why is subtract missing? Yep.
You can just store immediate as a negative value?
Exactly. So I don't need a subtract because I can just make my immediate be a negative value since it's already treated as a 2's complement number. Okay? So if we go back for a second to understanding how we interpret this immediate, what's going to happen is we're going to take the 12 bits that are encoded into our instruction and we're going to sign extend them. Okay? So you can represent both positive and negative numbers as long as they fit within a 12-bit encoding. All right. The last thing I want to mention about these types of instructions is the shift instructions. So the shift instructions are only going to use the bottom 5 bits in order to specify how much we're shifting. So they're not going to use the full 12 bits available, of our constant. And why is that? Why am I only using 5 bits? Yep.
Because the thing you're shifting will only be 5 bits.
Because 5 bits can specify how much of a shift?
32.
Yeah, so from 0 to 31. So beyond that, I've already shifted out all of my data, so it doesn't make sense to support shifts of more than that. All right, so let's take this example now and see if we can go ahead and implement this using RISC-V instructions. All right, so I've got this, C expression, which is telling me to do, addition, right shift, subtract. Now, we don't have, some crazy complicated instruction that's going to do the add, the shift, and the subtract all in one, right? So what I need to do is I first need to split this into basic instructions. So if I have an expression like this, I'm going to actually think of it as 3 different steps. So the first is I'm going to take B and add 3 to it and store the result of that into some temporary register. I'll then take that temporary register, shift it by C, store it in another temporary register, and finally I'll subtract that one and I'll store that result into my variable A. Okay? So what's that going to look like in our RISC-V instructions? Let's for now assume that all of my values, including my A, B, and C, as well as my temporary values, live in registers. Okay? So the translation of this would be this. I basically have an add immediate, which takes B and adds 3 to it, stores it into X4, which is the register that I'm using for my T0. Then I take the X4 and I shift it to the right by the bit specified in X3, which is my C variable. And finally, I subtract 5 from that and store it into X1, which is where my A variable is being held. Any questions about that? Yes?
How do you get a value into the register to begin with, to then use in a computation?
So, for example, let's say, I wanted to put the constant 3 into a register. I could do an add immediate with the X0 register, whose value is always 0, and my immediate being 3, and that would get my 3 into the register. And from there, I can then do the following operation with it. And we'll see other instructions for loading larger constants as well in a minute. Any other questions? Yeah?
I think I missed this from earlier, but what's the advantage of using add I over add here?
So add I means that you're actually embedding the constant that you're trying to add into the instruction itself. So you don't have to load it into that constant into a register. Instead, it's directly in your instruction. So I can say, if I want to do x gets x minus 1, I can do add I, x1 minus 1 gets stored into x1, rather than first having to load minus 1 into some other register and then doing a regular add operation on 2 registers.
And what's the benefit of doing that?
It's fewer instructions, so it's more efficient. Okay. So, as I just mentioned, sometimes we want to handle constants that are larger than 12 bits. And so for this, we provide yet another instruction type. And the way that this instruction looks is that you've got a 20-bit constant in here, because the only other pieces of information that you need are your opcode and your destination register. Okay? So the way that we interpret this long constant is we actually allow it to represent a 32-bit value, and so we take the 20 bits, they actually become the upper portion of our 32 bits, and then we append 12 zeros to the bottom. So let's take a look at an example of, how I would load some large 32-bit constant into a register using this load upper immediate instruction, which can handle a 20-bit constant. So specifically, let's say I want to load this cafe 0123 into my register X3. The way that I would do this, I'd have to actually split it into 2 operations. The first would be load upper immediate of my 20-bit constant, which is the top 20 bits of my of the value I'm trying to load, which is cafe 0. I would load that into X3, and that's going to result in X3 having this value with 12 zeros appended to the end of it. Okay? So then I can do an add I instruction, because now my constant fits into 12 bits, and so I'm going to add my 1, 2, 3, and now I have the value, 32-bit value that I wanted in my register X3, which I can then continue to work with. Okay? Yes?
Or does the load upper immediate automatically transfer the constant into the 20 most significant bits?
Yes.
Okay.
That's the definition of how the load upper immediate instruction works. Yeah.
Why is this specific number 12? Why the code doesn't fit in 12 bits?
So the 12 bits is for the, if you recall before, the register immediate type of instruction can only support a constant or an immediate value of up to 12 bits. Okay, so I couldn't have said add I of this whole humongous number because that wouldn't fit into my instruction. But I can say add I of just the 0x123, which represents 12 bits. Okay? All right, so the next type of instruction are load and store. And as we mentioned, these are used in order to move things back and forth between memory and our registers. So a load instruction takes something from memory and puts it into a register. And we basically have just a single load instruction that we're going to work with. It looks like this. And so what is this telling us? This is telling us that we want to load into register X2 the value that comes from memory that's computed by taking the sum of the contents of my register RS1 plus this immediate constant. All right, so if I look at this example here, this is telling me that I'm going to take the contents of register X3, add 4 to it. That's going to be the address of the location in memory that I'm going to access, and then whatever is stored at that location in memory is going to get loaded into my X2 register. Okay? So just like the register immediate operations, we have 12 bits of constant available for our immediate. And so once again, our 12 bits are going to get sign extended in order to produce this 32-bit value that gets added to our register. And the RISC-V actually supports a few other types of load instructions, but we're not going to use them. We're only going to use this one basic instruction, which loads an entire word or entire set of 32 bits at a time. Okay? So just like this load instruction, we have a store instruction, which is the store word, and the addressing The addressing works just like it did for the load, where we're specifying a base register plus an offset in order to compute our address. Yes, you had a question?
It is loading from the memory a word of 32 bits?
Yes. So remember that our addresses are always pointing to 32 bits at a time. Okay?
It first adds with the offset and still has a 32-bit word, and then puts that 32-bit word.
So for example, suppose that my address was 0x100. What it's telling you is that it's going to load everything that's at address 0x100, 101, 102, and 103. It's going to load 4 bytes worth of data into this 32-bit register. But I only specify load, what's at address 100, and by default, that's going to load 32 bits.
Wouldn't that load 16 bits? Because we're taking four things of 1 byte each. 4 by 4, 16.
No, a byte is 8 bits.
Oh, my bad.
Okay. All right. So once again, we compute the address like this. Now, who can tell me why might I want to add, this immediate constant to a base register in order to figure out what my address in memory is going to be?
You have an array.
Yeah, exactly. So the array could point to the base of my array, and then I use this constant in order to index into that array. Okay. So once again, there's other store operations in the RISC-V, but we're only going to use the store word operation. Okay, so now we're ready to do a little bit more in our RISC-V instructions. So going back to our original example where we had our variables stored in memory, let's see how we actually go ahead and implement this using RISC-V instructions. So here we have a little bit of pseudocode of what we need to do. So the first thing we need to do is we need to load the variable x into some register. Let's say we're going to load it into x2. And in order to do that, we first have to get the address of x, which is 1008, into some other register. And then we need to load the contents of memory pointed at by this other register into this x2 register. So it's actually going to take us a combination of a few instructions in order to get that x variable into a register. So specifically, in order to load 1008 into some register, I first am going to do a load upper immediate of 1, and then I'm going to add 8 to that in order to get 1008 into my x1 register. And now that I have the correct address in my x1 register, I can do a load word operation with a 0 offset, and so that's going to take the contents of 1008 and store them into register x2. And then after that, I'm going to subtract 37 from x2. That's easy. And finally, I'm going to store the result into 1000C. Now, I already have 1008 in register x1. So instead of doing another load upper immediate instruction, I can simply say store this into the address that's computed by taking the contents of x1 and adding 4 to it. Okay? All right, so finally, we have our control instructions. So control instructions allow you to have the PC not go just to the next instruction, but go somewhere else. And so we have two different types of control instructions. We have conditional instructions, which are branches. So like this example here says, branch less than. If x1 is less than x2, then I'm going to branch to label. Okay? And so the way that this is going to work is I'm going to perform this comparison. If the comparison is true, then I'm going to add this immediate constant to my PC. Otherwise, I just set my PC to be PC plus 4, which means point to the next instruction. Okay? And like our other instructions, we have 12 bits available for our constant, and so that means that this immediate has to be encoded into 12 bits of our instruction. And so what that means is that these branch instructions are limited in terms of how far away from my current PC I can jump to. Okay? And so the maximum that I can jump either is plus or minus 4 kilobytes. All right? So in addition to the branch less than, we have a bunch of variation of branch instructions, and here we list all of them. And so just before we finish up, in addition to branch instructions, we have what we call jump instructions. Now there's two differences with the jumps versus the branches. The first is that these are unconditional. Okay? The second is that they allow you to jump further than the branches do. So for now, you can kind of ignore this link part, but basically it turns out, which we'll see next in next lecture, that it's sometimes useful to save the value of the PC in some register. And so what this instruction actually does is two things. It stores PC plus 4 into RD, and then it changes the PC to go to PC plus immediate, except that now this immediate is actually encoded using 20 bits in our instruction. And so that means that we have a range of plus or minus 1 megabyte rather than just the smaller range that the branch supported. Okay? And then the last instruction is, suppose we want to do a really huge jump. We want to specify an address using a full 32 bits. And so for that, we use the JALR instruction, which stands for jump and link register. So you're specifying the address that you want to go to in your register. And just like our loads and stores, you can also have an offset from that register. And so what this is going to do is it's going to take the value in RS1, add the immediate constant to it, and that's going to be the value that's loaded into the PC. Okay? So let me just finish with this slide very quickly. So just a couple things to make things easier for us is that in general, instead of thinking, even though these instructions all translate into binary, we're going to write them in what we call an assembly. So we're going to have these mnemonics like add x1, x2, x3 to tell us you know, what we want rather than the binary representation. And we have a special program called the assembler, which is going to convert this mnemonic to the binary representation. The assembler also does two other things. One is that for things like branches or memory locations, it allows us to actually use a label, and it'll figure out what that immediate constant needs to be in order to access the correct location or to get to the correct location in memory. And finally, it also allows us to define pseudo instructions. So instead of, you know, even though I could specify something like add I x1, x2, x0 to mean put the value of x2 into x1, it's easier to think of it as move x1, x2. And so there's a pseudo instruction which just gets translated into this other instruction over here. Okay? And so with all of that, at this point, you're able to write any program. And so if you look at the last slide of today's lecture, you'll be able to basically go through how you would actually implement the GCD code using RISC-V instructions. Okay? That's it for today. Thank you.